So in the previous two videos, I discussed how to simulate a three-phase controlled rectifier, bridge rectifier. In that case, we specified the value of firing angle alpha manually and then analyzed the circuit behavior. At this point, we'd like to design a closed loop control that will determine the value of firing angle alpha depending on the load characteristics. Say, for example, we want to have a load with a certain ramp and a DC value, and we will want the controller to decide for the firing angle. So to start with, I will take some more components like let's first go into the PLECS environment and define some of the outputs here. So here you see I'm measuring the DC current and giving us ID actual, which is the instantaneous value of DC current. I take two other outputs specifying the line-to-line RMS voltage or line-to-line voltage in general, and also the line current here. So we get out of it and land in the Simulink environment. Let's now build a reference current first. So for my purpose of closed loop control design, I will take a DC load current with a certain ramp. I will define it here. So let's start with a ramp. Okay, since I am in MATLAB environment, or I can also type it here. Ramp, take this ramp, and I would like the simulation to look a little tied up. That's why let's take a subsystem, create a subsystem out of it. I'll change the canvas color to gray, and then let's start building the reference waveform. So for the ramp generation, I would say let's take it is the reference current waveform. I will take the peak of the DC current, that when it is in steady state, I would say start with 1 milliampere. I want the ramp to start at 0.1 seconds. Ramp end, then let's say stop it at 0.5 seconds. Of course, it is not there. So ramp slope, I would say it is I ref divided by difference of the two times. That means a ramp end minus a ramp start. So this is the rate of change of currents at which the characteristic curve will be built up. I'll show you shortly how it looks like. It will be clear instantly. Let's start with this. So slope, I said a ramp slope. Start time, I'd call it ramp start. And initially I want the output to be 0. So they're giving a warning because I didn't initialize the parameters yet. To visualize the present status, let's take a scope and see how it looks like at this point. Simulate. And it's not coming up. So let's see where the problem is. It seems to be here. It should be a division. So once it's done, so you see the ramp starts at 0.1 as specified as the start time of the ramp, and then it increases with the rate. It should be, let's calculate what's the rate. I will take a delta, specify the time to be 1 second. In that case, we have to specify the simulation time greater than 1 second. So if we check delta, and we need to see the value 2500. So that means in 1 second the value of the current change is 2500. Ignore the negative sign before it, it's the order of the cursors. That means if we now check our value, that means ramp slope, as you see here, it is 2500. The setting is okay. The only thing remaining is that we need to have a steady state where the increase is then stabilized and we see a ramp first and then a DC level. Should be specified by the IREF, which is 1000 ampere for our case. So at this point of 0.5 seconds and 1000 amperes, it should flat. So for that we need another ramp. I will copy this. I will need a summation block. Let's add them too. The only change that I need to make here is to take the negative of the slope, and then a positive and negative slope will make the slope 0. This is what I mean. Is it not too fast? Is this the only one? Ramp start? Start time. Okay. Now, of course, I need the negative slope after the ramp time ends. So I need to select ramp end. And then let's simulate. Yes, this is what I meant. Is at the beginning, I specified the ramp start is 0.1 second. After this specified time, there should be an increase of currents 2500 amperes per second. It's here. And after it reaches that steady state, it should be at 1000 amperes, which we see here. Yes. So proceed on. Let's build that PID controller so that our generated current on the DC side tracks this curve. So this I would name as IREF, and I'll take a PID controller. From that PID, I will use only the PI part of it. Form is the parallel part, and for P part, or the proportional part of it, let's take a variable KP, and for integral part, let's take it KI. Apply. Okay. So here I would say PI controller, KP, I would take 5, KI, I would say 150. Don't ask me how to calculate these values yet. We can discuss about them later, but for this moment, let's take them as trial and error method. We'll adjust them in future as needed. There's a PID controller, there's a PI controller specified here. Now, not yet here, the PID. So we need another summation block before the PID controller. And for an input, we will give them as a negative part, which is the feedback signal of PI controller. And it would be our then ID back true with the feedback signal. Let's connect this one, and the output of that summation block goes to the PI controller, and at the output of the PI controller we add a gain, and the gain value is 1 by, we need to include the DC voltage level. We need to normalize that output of PI controller, which is a voltage, by the DC voltage, which is 1.35 times value of the converter voltage, which is Vs. We need to normalize by that voltage level. I will zoom it so that we can see it better. And then we need to figure out the value of the alpha. So for that we need a saturation block. I'll tell you why it's needed. Just a moment. Cause saturation. The upper value of the saturation is 1 and lower value is -1. Now why is it so? If you remember, the output voltage for this controlled three-phase rectifier bridge, VDC, is equal to 1.35 times, maybe I write it here, VDC is equal to 1.35 times Vs, which is in terms of line-to-line RMS voltage, times cosine of alpha. So this is where is it gone? Oh, okay. Anyway, so this is VDC then is divided or normalized by that 1.35 times Vs, and we want to feed it to a trigonometric function, which is the arc cosinus. So I take a trigonometric function block, name it arc cosinus A cos, and that would be our alpha. So I'll name it alpha. To visualize this thing even much better, let's take a scope. Before taking the scope, let's take another gain. And since visualizing or for understanding it better in terms of degrees, let's take 180 by pi. Effector, connect it here, and we need a scope. Okay, let's get out of it. I'll take another scope. We need a multiplexer. So this is alpha. This alpha would be then connected to the converter block here. I need the actual value of the current as shown. Let's make some space. It's too much maybe. So I measure the value of the DC current, feed it to this block for the controller block, and then it generates the firing angle alpha. Let's name this firing angle generator. I can also take another block here, which I can call IREF, so reference current, so that I can better visualize both the current waveforms in one scope. So I'll take a reference current, I'll take the actual current. So I need in total 3 windows. One would be for the current. Let's take 4 windows. So as I mentioned, one would be for the current, one would be for the AC connection voltage, one would be for the AC side current, and another should be for the firing angle. We want to also monitor that firing angle. Again, for the firing angle, let's take a block here to convert it to degrees. So 180 divided by pi. If everything goes fine, let's start this ramp. Also, let's activate the converter at ramp start. So, do we have everything here? It's defined. So load current is, as a load resistance is 0.5 ohms, and we have considered an inductance of 5 millihenries. Other parameters are unchanged. Let's run and see the results. So see, the controller is actually tracking the currents. If you see here, the red is the reference current and the green is the produced DC current by the converter. So the controller is doing quite a good job at this case. Before I go into details, I would like to check the values. So I'll take a mean value and also take an effective value. Let's set our cursors to one period of, that is 20 milliseconds. So if I want to check the mean value of the current, it's exactly 1000 amperes. So the tracking is working fine. We had the connection voltage of 1.5 kilovolts, which is the second scope here, which is also correct. And DC current is, it seems it's 818 amperes. DC current, if I zoom into, so this is the DC current, you see, with the harmonic part, of course, inside it. And the last one is the firing angle. So see, the tracking is not the best, I would say. So it depends on the adjustment of the PI controller parameters. Let's take some other values like 0.1 of the proportional gain and check the tracking. So it took some time to open. So now you see the value of the firing angle. The last window of the scope is quite good at tracking performance. So it's around 75.5 degrees when it's continuously pulsing. And here also the current tracking is also quite good. So the topic of how to determine the value of Kp and Ki could be a topic for another topic. It's a for control engineering topic, but at this here, the idea was to implement the converter system for a closed loop load characteristics. Now, for example, if we want to change the load characteristics, like take it 500 amperes, let's check if the response is good enough. So what we see here is again the tracking is successful. We have a considerable amount of ripple here, but this could be reduced by adjusting the value of the PI characteristics and also by increasing the inductance value. Like if we take a 10, it should be filtered out. Yes, a little bit better, but it just needs a fine adjustment. Let's take back 5 millihenries again and increase the peak value of the current, the DC current. Now let's take 1.5 kiloamperes and see the response. So it seems the tracking is still successful. So if we quickly check the values for a time period, let's take a mean value. Delta should be 0.02. And the mean value is then exactly 1.5 kiloamperes. So this is how we implement the closed loop control for a three-phase controlled bridge rectifier. Now, of course, if you look, we had a completely ideal converter systems. We didn't consider any lossy element like the transformer, like the grid impedances, etc. Even inside the bridge itself, we didn't consider thyristor forward voltage, thyristor on or slope resistances, or any thermal consideration, nothing at all. So these topics will be discussed in future videos. That means we will consider using this configuration. We will extend the explanation for a more realistic converter systems. We will include grid impedances, include the impedances of the transformers, and also the parameters of the thyristors itself, and design more advanced converter. And stay tuned for that, and thank you for watching.